I want to discuss a formulation of the refined local Langlands correspondence or conjecture for disconnected groups. So it's supposed to be a framework in which to discuss disconnected groups alongside connected groups in as far as the Langlands conjectures are concerned. And I want to focus today on the local aspects of this. So why may you be interested in this? On the one hand, there are naturally occurring groups that are disconnected. Most basic example is the orthogonal group, which comes disconnected. But also, if you're just interested in connected groups and start with a connected group, you can very easily perform a construction that gets you out of the setting of connected groups. You can form the centralizer of a semi-simple element, which may end up being disconnected, or you may end up having to deal with a Levy subgroup and then the action on this Levy subgroup by the relative Weil group. And so you have to consider the semi-direct product of those, or maybe a twisted form of this situation where there is no longer a product structure involved. And so you'd like to be able to address this. And in such situations, oftentimes people have had some workarounds, like when you're taking a centralizer, maybe you're going to make an assumption that the derived group is simply connected, so the centralizer is connected or reduced to this case. So what I would like to do is have a general framework where no such ad hoc constructions are necessary. So I want to explain what I have in mind by first reviewing the case of a connected group. So let's begin with this. The connected case. So the basic setup is going to be F is going to be a local field, and I'm going to assume that it has characteristic 0, although it's certainly worthwhile thinking what happens when one drops this assumption. And G is going to be a connected reductive group over this field, and we'll be interested in understanding the set of irreducible, admissible, complex representations, so the classical setting. And for this, let me take the Galois group of F with respect to some fixed algebraic closure. W is going to denote the Weil group. And for Langlands parameters, I'm going to use the Weil group or the version of the Weil-Deligne group where we take the product of the Weil group with SL2C. So depending on whether F is Archimedean or non-Archimedean. And going to form the complex Langlands dual. And then the L group is the semi-direct product of the complex dual with the Galois group. So this is the usual setup. And then I'll just briefly remind you of the conjectures in the connected case. So first, the quasi-split situation, which is the easiest to state. Then we have a one-to-one correspondence, but maybe let's say an injection, at least an injection, and in the non-Archimedean field, a bijection between this set and the set of what sometimes is called refined Langlands parameters, where the first piece is a Langlands parameter in the usual sense, so a homomorphism from this local Langlands group to the L group of G, subject to the usual properties that I don't want to recall. And then the second part is an irreducible representation of the component group of S phi bar, where I'll denote here by S phi the centralizer of phi in G hat, and by S phi bar, is this okay or too low? I don't know. Also, I should ask is if the size, the font is okay or needs to be changed. People seem to agree. Okay, thank you. S phi bar will be the quotient of S phi by the Galois fixed points in the center of the dual group. And all of this, I ran out of room here, but all of this is taken up to conjugation by G hat. Okay, so this is the quasi-split setting. And let's see, do we have more chalk? In the general setting, then I'm going to still take G to be quasi-split, but this is not the group I'll be interested in. I'll also take a twisting element in the Galois cohomology of G modulo its center. And this is going to provide me with an inner form of G, and this is the group I'm interested in. So I want to now understand pi of, so the set of irreducible representations of this group. And let's first assume that this twisting cocycle lifts to the Galois cohomology of G itself. Then the statement is again easier to state, and it goes back to Vaughan, who then says that there should be the same kind of picture as above, an injection of this pi G, which is bijective in the non-Archimedean case, to the set of pairs, or phi is exactly as before, and rho now is slightly different. It's an irreducible representation of pi 0 S phi without the bar, where we're no longer dividing by ZG hat, but now we're requiring that instead of acting trivially, this ZG hat gamma acts by a certain character. And this character corresponds to Z under a map that comes out of the work of Kneser and Kottwitz, which is a map from the Galois cohomology of G to characters of the Galois fixed points in the center of the dual group. Yes. Does this one go more up? Oh, it does. Yes. Okay. Does that help now? The question is, how am I? But maybe I'll worry about this later. There's the straps. Okay. Okay. So this is in the setting, but then I'll have to push it down again because I have to write. Is that okay? I'll try to write high. And now, if we drop the assumption that this Z lifts up to H1G, we have to use what Langlands and Rappaport call a Galois gerbe. This comes from the notion comes from the Langlands Rappaport paper 1987, when they were studying the special fiber of Shimura varieties, and their notion of a Galois gerbe is a very down-to-earth notion, which is just an extension of the Galois group by an algebraic group or maybe a pro-algebraic group. When you are in this situation, you can always consider the cohomology of this group valued in G instead of the cohomology of the Galois group. And if you demand that the band U takes values in the center, then there is a natural map from this down to the cohomology of the quotient. And on the other hand, there is an injection of the usual Galois cohomology in here. It's formed by those cohomology classes which are trivial on U and hence factor down to gamma. So this picture just works for any Galois gerbe, but what we actually want are two things. One is that the map down to this adjoint group is surjective, so that we can lift the class that we have here to a class here. And we also want a variant of the Kneser-Kottwitz map, which is now going to explain this bigger cohomology in very similar terms. And what ends up being the target here also has something to do with the dual group. So let me explain down here what it is. So when we take the dual group, we can take its universal cover. And universal cover in the analytic topology, which means that if the dual group is semi-simple, we just take the algebraic simply connected cover. But if the dual group is a torus, we end up with an affine space as a cover. And in here, one of the things we have is the Galois fixed points in the center of the dual group. And we can take the pre-image, and I'm going to denote this as the center of G bar hat, and then plus, which would mean not necessarily Galois fixed, but its image down in G hat is Galois fixed. And this is what ends up being the target of this Kneser-Kottwitz map in this situation. Okay, so we would like to have this picture, and in fact, we have this picture. So I did this some years ago when the characteristic of F is 0, and Peter Dillery extended this to fields of positive characteristic, where now this notion of Galois GERP is no longer sufficient. One actually has to deal with the more abstract notion of a GERP, but this can be done. And then one has this picture. Okay, so now we are come back here and would like to have the corresponding conjecture. So the question is, what is going to be S phi? And somehow this map already gives us a suggestion what it could be. We have the group S phi here, and we just take its pre-image in the universal cover. And then the conjecture is the same. I'll write it down. That is helpful. Thank you. So the conjecture is now that as before, we have a parametrization in terms of tuples. Phi is as before, and rho is an irreducible representation of pi of S phi plus using the universal cover. And then using this version of the Kneser-Kottwitz homomorphism, we want this Z G hat bar plus to act by the character Z. Okay. So this is the picture that parameterizes representations. And we want one more thing. We want character identities. Because this is going to tie the local picture into the global picture, in particular the trace formula. So the character identities are going to work in the following way. We have the parameter. We're interested in a particular parameter here, which Witt again likes to call the last name of the representation. So this is the name of the representation, and it has a last name and a first name. It's written in Asian convention where the last name comes before the first name. And we're going to ask that it is tempered. Of course, one also expects character identities for non-tempered parameters, but then the Langlands parameters are not the correct thing to consider. One has to consider Arthur parameters. So in order not to complicate the language, I'll stick with Langlands parameters in the tempered case. And then when we take an element in S phi, we can consider its centralizer in G hat, and this leads to a quasi-split group over F, which is called the endoscopic group, and it's in such a way that there is a map of L groups that factors the parameter. Okay, now strictly speaking, this is not true. There's not always exist a map like this. And even if it did exist, it would not be canonical. So the actual thing that is true is that there is a canonical double cover of this endoscopic group, and it comes equipped with the canonical embedding of L groups. So this is now completely canonical, but I don't want to talk about double covers in this talk. So let's just pretend that those things are the same and ignore this, part. And then this is what we would like. Would like the following virtual character on the group G, where I'm summing over all representations with the same last name, and I'm forming a virtual character. This is the Harish-Chandra character of pi, and I'm using the first names in order to form a virtual combination of those. This is equal to, so this is in representations of G with the given last name. I can perform the same thing for H with the same last name. And here I'm using the dimension of the first name. So I want this kind of identity where F mapping to FH is the so-called transfer of test functions. Okay. So this is the picture that this is the picture in the connected setting that I would like to generalize to the disconnected setting. What kind of F? So I'm thinking of F as being a compactly supported smooth function on the rational points of G. Well, but I'm using G sub Z bar, I guess, for the group that I really care about. And this is supposed to go to the same kind of function on H. Yes. Other questions? Oh, thank you. Yes, Tony. No, GZ bar. I'm interested now in G of Z bar. And this is reflected in the Z here. Did I forget to put the Z bar here as well? I did. Yes, sorry about this. Now I'm interested in this not quasi-split group. Exactly. All the G's are GZ bars here. Thank you. Yes. Okay. Other questions? Okay, so on the way to disconnected groups, there is actually classically a theory that addresses what should happen in the disconnected setting. And this theory is called twisted endoscopy. And I'll just give a very cartoonish sketch of what twisted endoscopy is concerned with. So here we have a connected reductive group. But we also have an automorphism acting on it. And so now one is considering the pair of the group and the automorphism. And for example, the notion of conjugacy, which would look like this, is replaced by the notion of twisted conjugacy, which looks something like this, that instead of multiplying on the left and by the inverse on the right, you multiply on the left, but then by applying the automorphism to the G and then on the right by its inverse. And then the notion of a character, which morally speaking is the trace of G on the representation pi, is replaced by the notion of a twisted character, which should be the trace of not just pi G, but pi G composed with a certain automorphism. And this automorphism is an isomorphism between the theta twist of pi and pi. So this theory is concerned with representations of G that are stable under theta. Theta acts on all the representations. Some of them are fixed, some of them are not. Those that are fixed are of interest. And then the fact that they're fixed, their isomorphism class is fixed, is witnessed by the existence of such an isomorphism. And how this captures disconnectedness is by considering the semi-direct product of G with the cyclic group formed by theta. And inside of here, we have the distinguished coset of theta, and the group G acts by conjugation on this whole group, and it preserves the coset. And if you see how it acts on this coset, well, it's this action if you just restrict on the G part of the coset. So in this way, disconnectedness is somehow addressed by twisted endoscopy. But so what I propose is in some way a modification or a language on top of twisted endoscopy, which is there to address the following problems. So the first problem is that of normalization. And it has two parts. There is a spectral part, which is the choice of this I theta. This isomorphism I theta, of course, by Schur's lemma, it will be unique up to a scalar. And then if theta is a finite order, this scalar can be even made to be a root of unity of that order. But beyond that, there is this ambiguity. And how do you resolve this ambiguity? In some situations, you can resolve it by ad hoc means. Say you have a quasi-split group and a generic representation, then you can use Whittaker data to resolve. But in general, there is no ad hoc resolution to this. So this is one problem of normalization. Another problem of normalization is that of transfer. There is again a transfer map. F goes to FH in this twisted setting. And again, this transfer is well defined up to a scalar. And if you want to write precise formulas, both of these ambiguities are a problem. So this is the first problem. And then there is a second problem, which is that of non-cyclic component groups. Imagine you have a disconnected group whose component group is not cyclic, and you would like to study this. Well, you could study things component by component using this theory, but then the question is, how do those components interact with each other? If you solve your problem per component, in the end, you'd like to have some coherence of these solutions. And the third problem, which is less of a technical mathematical problem and more of an aesthetic problem, is that of language. You'd like, or I would like, to have a language that uniformly addresses the connected and the disconnected case in a way where ideally you don't even notice whether or not you're dealing with a disconnected group. So I wouldn't want to replace the notion of conjugacy, the notion of character. I would like to say, well, I have a disconnected group. It has action of conjugation. It has characters. What can you say? What can we say in this language? Now we come to the same problem that was avoided with the second. So is this the correct tool? Okay. Okay. I'll take my chances with this one for now. Also, another question, is there a clock somewhere? Oh, okay. Good. Okay. So now let's come to the disconnected case. And the first thing I want to do is I want to introduce the kinds of disconnected groups that I would be considering. So there are two assumptions. The first assumption is that G tilde is an affine algebraic group whose identity component, which I'm going to denote by G without a tilde, is reductive. So ideally, I want to stop here and make no more assumptions. However, at the moment, I have to make another assumption that this thing is geometrically split in a certain sense, which would mean that if I go up to the algebraic closure, there exists an isomorphism between the connected component, base change to the algebraic closure, semi-direct product of finite group A, and this finite group A is a geometric component group, acts on G over F bar in a pinned way. It preserves a pinning of this GF bar. So a Borel subgroup, a maximal torus in it, and a collection of simple root vectors. This doesn't have to happen rationally, but it has to happen geometrically. So these are my assumptions. And let me note that if the connected component is adjoint, then assumption 2 is automatic, but not otherwise. There certainly do exist such disconnected groups with non-adjoint identity component where assumption 2 fails. So here are some examples. The orthogonal group is fine. And another thing that is also fine is what I mentioned briefly in the beginning. If you have a Levy subgroup and you're interested in the semi-direct product of this Levy subgroup with its with the action of this relative Weyl group, this is fine. And also certain twisted forms which are necessary. And I'll explain what this means in about 5 to 10 minutes. This is also okay. However, what is not okay, a very simple example where it is not okay, is the normalizer of a torus in SL2. So this assumption too can fail in the most simple situation. In some sense, an undesirable assumption. The action of A does not have to be faithful, no. In fact, it is perfectly okay to have a direct product with A. Maybe not very exciting, but certainly allowable.
Stronger assumption that exists this semi-direct product protection, or what is the action spin?
No, these are both. So no, I think the semi-direct product assumption is really the bad assumption. You can always, in any situation, you can create a section that preserves a pinning. That would involve making certain choices. If you have a non-trivial center in the connected component, you're of course welcome to make these choices. And then you're going to have a non-homomorphic section that preserves this pinned, the pinning that you want. But it's not going to give you a semi-direct product structure. So the semi-direct product is really the key assumption. Right. So in the quasi-split case, you use a pinning and use a TITS. So it's a multi-step thing that's not terribly complicated. So first you realize this WGM as a subquotient of WGT, where T is a minimal Levy. And then from WGT, you have a TITS section coming from a pinning. And then you say that you check that when you restrict this section to, and this TITS section is not multiplicative. That's a key thing in the theory that shows up everywhere and leads to a lot of discussion. But what you show is that when you restrict from WGT to the subgroup, whose quotient is WGM, then this non-multiplicativity error ends up being valued in the center of M. And so as far as the action of this on M is concerned, there is no error, and you actually get an action. And moreover, the subgroup that you're going to eventually divide out acts trivially. And so that gives you this semi-direct product in the case where G is quasi-split. When G is not quasi-split, there is no such semi-direct product, which is why I put the twisted there. But you can form a twisted version of this, which works in general. And maybe towards the end, if I have time, I can discuss this, or privately. One of the key applications of this whole story is to connected groups when you want to extend the refined correspondence from discrete parameters to tempered parameters. All of this comes in when you try to normalize into 20 operators. Other questions? Okay, so for the first thing we'll do, let's classify the possible G tildes. This, in some sense, works in a parallel way to the classification of connected groups. So very crudely, there is the split case, which means that we have a G semi-direct product A, and this happens over F, not over F bar, and moreover, G is split. A split group, semi-direct product, some finite group that preserves a pinning. And then we have forms. And the forms are classified by the Galois cohomology of the automorphism group of this thing. So to understand the forms, we need to understand the structure of this automorphism group. And it turns out it has three pieces. So the first piece, we have the adjoint action of the connected component onto this disconnected group. So that is a piece in here. And then we also have the second piece, which are automorphisms that preserve a pinning. But let me say exactly what this means. So these, first of all, any automorphism of G semi-direct product A, of course, preserves G because G is the identity component. But we want more than preserving G. We want them to preserve a pinning of G. But that's not quite enough. We want them also to preserve the subgroup A, which is a subgroup from this semi-direct product. So these two are exactly as in the connected case. You have the action by inner automorphisms, and you have the pinned action, okay? But there, it turns out that there is a third piece, which is not visible in the connected setting. And that is the one cocycles of A valued in the center of G. These also go into the automorphisms of this. And how do they go in here? When you have such a one cocycle, you can map it to the automorphism that sends G times A to Z of A times G semi-direct product A.
G decided A is G base change to FR?
No, so this is a split. I'm in the situation where I have a split situation and I want to understand its forms. So this is now a disconnected algebraic F group, and it has an automorphism group, which is also an algebraic F group. And with respect to this, I'm taking the cohomology.
G tilde is G semi-direct A.
Exactly, because I'm breaking this up into the split case and then the forms of the split case. So I want to understand how can I get all possible G tildes in a usual process of split and then twisting the split. In what different ways can I twist? Turns out you can twist in three different ways. In the connected case, you can twist in two ways. First, you go from split to quasi-split, and then you go from quasi-split to an inner form of quasi-split, which is what I was doing when I was putting the subscript Z bar. I took a quasi-split group and then I twisted it by the Z bar. Here you can take a quasi-split group and then you can twist in this way or in that way. And so first of all, what turns out is that 1 and 3 commute in this automorphism group. Their intersection, they are not disjoint, they have an intersection, which can be understood from the point of view of 1 as the quotient of the center by its A fixed points, and from the point of view of 3 as the one co-boundaries of A valued in ZG. So that's some kind of a predictable meeting place for 1 and 3. And moreover, 2 is a complement to the product of 1 and 3. And that gives you the entire automorphism group. Right, so now this tells us that if we start with a split disconnected group, we obtain a general one by twisting in steps. Twisting using 2 is going to give me what I may call a quasi-split disconnected group. What does a quasi-split disconnected group look like? It looks again over F as a semi-direct product of G and A, where now, so this is over F, where now G is quasi-split, and A preserves a pinning. And after I've done this, I have the option to twist either by inner automorphisms coming from the identity component or by this, such translations coming from the center. In which order I do this doesn't matter because those two commute, but I get to do it in either way. So this is going to give me something that I want to call inner forms. Say again? Right, so maybe I should say A preserves an F pinning, which means a pinning where the Borel is defined over F, the torus is defined over F, and the simple root vectors are permuted by the Galois group. Yeah. That's a very good question. So gamma, you can take A to be a constant group scheme, then gamma doesn't act on A. Or maybe in your particular situation, gamma naturally has an action on A, but then here you're going to end up with the gamma fixed points like this. And in any event, any point of A that's not fixed under gamma will then not be seen rationally. And so when you're studying harmonic analysis and take rational points, these components will be invisible. And then you can just simply remove them. You can pass to the subgroup where you have removed those components. And on rational points, this will be invisible. And so it's up to you. There is some flexibility in how you build the theory. So in the beginning, I can just assume that A is a constant group scheme over F. Or in simple terms, it's just the... No. I'm taking all possible automorphisms of this disconnected thing, whatever they may do. So this I'm not assuming. And so in the process of twisting here, these are allowed to act on A. They preserve A, but they can act non-trivially on it. And so A may acquire a gamma action, which is what would make the sense of me writing this. Now after I've twisted, I have a new situation where G has now become quasi-split. It used to be split. But also A has now acquired a gamma action. And when I take F points of this, I will only see those cosets corresponding to a gamma fixed point of A. But in fact, let me talk about rational points in 1 minute. Yeah, that's important. And then just finish by giving a name to those things. Let's call those translation forms. These are kind of the new things that weren't visible in the other setting. Let's see, I wrote on this already, so let me go here. Okay, and of course, maybe it's a little deflating to hear, but I'm not going to talk about translation forms today. I don't have much to say about them as of yet. I'm going to talk about quasi-split forms and inner forms. This is what I'll discuss as far as Langlands conjectures are concerned. Say again? Yes, but now quasi-split form has the meaning that you have a disconnected group which is semi-direct product over F, not just F bar, and the identity component is quasi-split, and A preserves a pinning. So that's the definition of quasi-split in the disconnected case. The existence, well, I mean, the existence of a split form is kind of guaranteed by condition 2. Condition 2 tells you there is a split form. Yeah. Okay. So today, if I just stare at G tilde, can I somehow see? I have not thought about this. Yeah, certainly a good question. Maybe, but I don't know. So today I'll talk about quasi-split and inner forms. Okay. And so my first order of business is to try and set up the conjectural framework with regards to parameters and first names, last names, and so forth. So what am I going to take? So I'll have G tilde to be G semi-direct product A quasi-split, which means, again, G is quasi-split and A acts on G preserving an F pinning. I can safely assume, yes, I can say it here. I was going to talk about rational points, so let me say it here. And then I'm going to take Z bar to be in H1 gamma of G mod ZG A. This is going to give me an inner form of this quasi-split group. So this is what I'm ultimately interested in, where, of course, the Z could be trivial, so I look at this. So let's look at rational forms. Sorry, not rational forms, rational points. So the rational points of the quasi-split group are kind of simple because we have a product decomposition over F. So this is all you get. It's, again, a semi-direct product. But the rational points of an inner twist, well, they're going to sit in an exact sequence like this, which is going to terminate with some subgroup of A, which I'm just going to name like this. But this, in general, has no distinguished splitting. And in fact, I believe that there will be situations where there's just no splitting whatsoever, although I confess that I have not computed an example where I've shown that the extension class is non-trivial, but I see no reason why it should be. Anyway, this is just a expectation rather than a mathematical statement. And so, but even if this were split by some non-canonical reason, certainly the situation doesn't give you a splitting. And so you have to now deal with representations here in this context. Okay. So the goal is to classify the irreducible admissible representations of the rational points of this group by, again, such first and last names, and also formulate character identities that are going to tie this local conjecture to the global picture. This is what we want to do. Okay, so what is the first question? Well, the first question is, what is the last name? Right? This is somehow the first invariant that A becomes twisted when you have an inner twisting. A can become twisted because you have G acting on G semi-direct product A on the whole thing. And so now that's right. However, it acts it acts trivially on the component group. However, if you look at the full component, the component gets twisted. The action on the component changes. And as a result, it may well happen that a component that had an F point when you were in the quasi-split form ceases having an F point. And moreover, if a component has an F point, it doesn't have a distinguished F point anymore, even though it did so in the quasi-split setting. And so when you look at F points, the quotient will in general be something smaller. And you can actually say exactly what this A of Z bar looks like. And the cleanest way to do it, if you imagine that Z bar lifts to some Z in the cohomology theory valued in G rather than G modulo something, whether this will be Gallo cohomology or this Derby cohomology, then this A Z bar becomes simply the stabilizer in A of the class of this Z in the cohomology you're looking at. So it has a very clean formula of what this A of Z bar is going to be. And it could in principle happen that A of Z bar is trivial, in which case you're back to a connected situation. Okay, that's easy, then we know what to do. But it can happen that A of Z bar is non-trivial. Okay, so here is I'm going to postulate something which may seem a little boring, which is that the L parameters for G tilde Z are the same as for G of Z. I'm not going to change the L parameters. In other words, I'll be looking at yes, I'm becoming lazy with the bars because I'm anticipating lifting Z bar to Z and then using that. But yes, these are the L parameters as before, which means I'm going to now define the L packet on G tilde Z bar to be simply all representations of G tilde Z bar whose restriction to G of Z bar meets the packet for G of Z bar non-trivially. Okay. No, I'm just declaring this is what I'm going to do. This is a definition. And now you could say, well, okay, we can end the talk here. Now we know how to associate an L parameter to any representation. This was super boring. Maybe we'll have a longer coffee break. But remember, the point is that I want to have a refined conjecture, which means I want to parameterize, to classify this set, not just break it up into chunks and classify that. I want to classify each individual piece. And so the challenge now becomes the following: is parameterize this set phi of G tilde Z in terms of the dual group and the Weil group somehow, and also formulate character identities. So the last name is not the issue. The issue is the first name. How do you associate first names to pieces of here so that in the end you have a bijection, or at least an injection of this whole set of irreducible representations into something that has to do with parameters and the dual group? And now you could, of course, challenge this postulate and say, well, maybe this is a too naive thing. Why do you do this? Isn't there something more meaningful you can say? But then you can consider the following situation, that G tilde is equal to A. In other words, G is the trivial, the identity component is trivial. So then what would you be trying to do? You will be trying to understand the irreducible representations of some arbitrary finite group using the arithmetic of F. And that's nonsense, because F and A have no relation with each other. Why would you ever expect this? And this is why this postulate seems like a reasonable thing to do. But then what do you do with first names so that you have an actual full parameterization of all the representations? And how do you tie this into character identities? Oh, but it's quite clear. So, but of course, this is a good question. Can packets possibly intersect? If they did intersect, they are going to be equal, because that's true for the packets on the connected group. And just from this very definition, you see that two such packets on this connected group are either disjoint or equal. But then you can say, under what circumstances are they equal? And this is the key question that actually answers something that seems like an unrelated question, which is how do you formulate first names? Those two things, although on the surface seem unrelated to each other, are actually almost the same question. And so this is what. Mm-hmm. It's perfectly possible. Yes. Right. So let me address this let me address your question while addressing the question of first names at the same time. Okay.
A, and then you take care of this A, that is
Well, why should the homomorphism be surjective?
A is a GLA.
No, I guess maybe you're right about this, that then you're going to have some extension. Maybe, yeah. So maybe there is an alternative way to think about this that will produce something different. That's quite possible. Okay, so how are we going to approach parameterizing this? Well, let's remember, I think is there a version of it on the board? It's now gone, but let's remember here that in the connected case, the classification looked something like this. So there was something related to this group S phi. And so now the question is, well, what should be the S phi group in the disconnected case, if you believe that something like this should generalize to the disconnected setting? And this is related to that's question about intersections of such packets. So here is, so let me recall that phi1 and phi2, two parameters into LG are equivalent from the point of view of this connected group. The definition is if and only if they're G hat conjugate. That's the definition. It doesn't depend on Z. This is true for any inner form. They have to be G hat conjugate. Okay, but then what is S phi? S phi, well, it was the centralizer of phi, but in terms of equivalence, this is just the group of self-equivalences of phi. If you're not just asking what does it mean for two parameters to be equivalent, but if you ask the slightly more refined question, what is an equivalence of two parameters? Well, it's an element of G hat that conjugates the one to the other. Then you can add what is a self-equivalence of a given parameter? It's this S phi. So now that's question, what does it mean for two parameters to be equivalent in the disconnected setting, which would mean under what conditions should two packets interact with each other, maybe intersect or maybe will directly lead to what should be S phi in the disconnected case. It should be the group of self-equivalences of the parameter. So we're going to again postulate or define that phi1 and phi2 from LF to LG are equivalent from the point of view of the disconnected group if and only if they're conjugate under G hat semi-direct product this A of Z bar. So the notion of equivalence classes of equivalence of parameter changes. Now, why is this reasonable? Well, now this comes to the question of maybe taking a representation of pi of the disconnected group and restricting it to G. It will break up into pieces, and these pieces could span multiple packets. What possible packets do we see there? Well, if phi tilde restricted to G as ZF meets pi phi1, then it also meets pi phi2 under this equivalence, and vice versa, which means this equivalence tells you, this notion of equivalence tells you exactly the kinds of packets on the connected group that a representation on the disconnected group can hit. And this you can see by looking at what are functorial properties of local Langlands correspondence for the connected groups. Intersection, thank you, are non-empty. Yeah, thank you. This is a functorial property of LLC for the connected group GZ bar. There is a very nice way to formulate functoriality of the local Langlands correspondence with respect to any F automorphism of the quasi-split group. When you think of L packets as spanning all inner forms, there is a very natural way in which to formulate this functoriality. And then this observation will come out of this. And so that would tell you that if two parameters are equivalent in this way, then they'll give you the same packet up there. And if they're not equivalent in this way, then they'll give you disjoint packets. But it also tells you something else. It tells you how to define S phi tilde in the disconnected case. So this is going to be the group of self-equivalences, again, of phi. And well, this is just going to be the centralizer of phi in the disconnected group G hat semi-direct product AZ bar. So the notion of self-equivalences changes, and it's a little funny that now, so let me make a remark. Now this depends on Z bar, whereas before it didn't. So the notion of equivalence of parameters didn't depend on the inner twisting in the connected case, but it does depend on the inner twisting in a disconnected case, because this inner twisting has the capacity of possibly shrinking the component group, and you need to take this into account. And now that we have defined S phi tilde, we are ready to write down yes. That's correct. If you know that you'd be dealing with a particular Z bar, you can from the beginning replace A by AZ bar and not worry about the rest. That is certainly possible. But now we're in the position to formulate the conjectural structure of this L packet up there that we wanted to classify. What does this, 5 minutes, goodness gracious. Okay. So now the conjecture is the following. First of all, when G tilde is quasi-split, the conjecture is that we're going to have this packet on G tilde be injecting into the irreducible representations of pi 0 S phi tilde modulo ZG hat gamma. And in general, in the inner forms case, I'm going to lift Z bar to a class, again, in this cohomology of this Galois GERP. Now I'm using a different kind of center here, but other than that, it stays the same. And then this is going to be parameterized by the irreducible representations of pi 0. Now I have a number of decorations. The tilde for the disconnected, but then the Z, because I have to take that into account, but then also a plus to go to the simply connected cover of the dual group. And this is it. So now we have succeeded in giving first and last names, and this resolves the following problems for the beginning. The choice of I theta is now baked into this structure. The dual site will dictate how I theta will be chosen. In fact, all possible choices of I theta are going to occur, and they're going to be accounted for by different members here. And secondly, we have interaction of components. This is also taken care of. Now, what about character identities? Well, the picture is exactly the same as before. We're now going to take an element in this new equivalence group for the parameter. We're going to form the same construction as we did before. This is the part where the language really doesn't change. This is going to give us a quasi-split group. We're going to have the same factoring of parameters as before. Let me not write it down again. And then we had another difficulty, which was that the transfer map needed to be normalized. That was the second problem of normalization. I know this is somewhat technical, so I'm not going to discuss any details of it. I'm just going to state as a theorem that this class Z normalizes the transfer. Okay, so there is something to be proved there. It involves using this Gerby cohomology on complexes of tori of length 2, but after you've suffered enough, it works. And then let me just say that the character identities conjecture takes the exact same shape as it does in the connected case. You just take the connected conjecture, you put tilde at a few places, that's the conjecture in the disconnected case, the same thing. So do I have half a minute or not? I don't know. So maybe I'll stop writing and I'll say verbally some indications for this conjecture. The simplest case is when you consider disconnected groups whose identity component is a torus. And in this situation, you can prove the conjecture, and it turns out that there is something non-trivial to check. It ends up having that you have certain extensions, one produced from the automorphic side and one produced from the Galois side, and you have to prove that these extensions are canonically isomorphic. And this seems a little crazy on the one hand because they're constructed in very different ways. On the other hand, they look so symmetric that it looks plausible. And so there is something that, and this is what ends up organizing connected components in the end. So there's something between the group and its duo that has to do with extension classes that is in synchronicity. And another more serious test is that of real groups. So this is currently work in progress with Paul Mezzo, where we study disconnected real groups where the identity component is adjoint. And we study discrete parameters, and we're in the process of proving that you can organize packets this way and character identities hold this way and so forth. There is also work of Yi Lu, who is a graduate student of Wittek Gan, on the global setting. So all of this is set up so that there is a global theory as well. In particular, would be interested in automorphic forms on disconnected groups and automorphic multiplicity formula. And using these first names, you can state a conjecture for the automorphic multiplicity formula, and the student proves it again in the case where the identity component is a torus. So that's the beginning of a global theory coming out of this. And there is another application to intertwining operators, which I mentioned, but since I'm out of time, I'm happy to talk privately about these things to whoever is interested. So I'll stop here.